Hello, everyone, and welcome to the Builder's Workshop. My name is Nathan, otherwise known as Old Man Builds. We got the Benny Factor here, and we also have Shawn Calderon here with us today. We should have Gerald joining us shortly. Guys, what's going on?
How you doing, Nathan? Hi, Shawn.
Doing
Hey,
great.
good to see you guys. Nice to be on, Nathan. Thanks for inviting me.
Oh, it's your show, man. I keep telling you that.
Oh, you're too kind. I'm having a hard time finding you. I can hear you. Oh boy. Oh, here we go. Okay. Sorry about that. I'm just going to get my presentation here ready for when you're ready. Right. Let me know when you can see.
Sorry, give me 1 second.
Okay.
Don't start your presentation just yet.
Will
the Mad
do.
Coiler. I love it.
I simply just want to let everybody know real quick, Shawn Calderon, and I'll announce this later too, has his own YouTube channel now. So congratulations, Shawn.
Thank you so much. I couldn't have done it without you guys. Nathan.
Yes, amazing.
You're my mentor.
So that was Shawn's right here. There's his channel address if you guys want to go over there and subscribe to him. And Shawn's going to start uploading onto his channel here with all of his experiments. So right on, Shawn. With that said, the floor is all yours, my friend.
Awesome. I'm wordless at all the kindness you've shown me. I appreciate that so much. And I appreciate you guys in the chat for coming here every Wednesday and listen to me ramble on about what's going on in my lab. But I just appreciate you all, guys. Let me see here. Can you see my screen?
Yeah, we can see it.
Okay. I'm not getting my arrow. I don't know what happened here. Sorry, 1 second. Okay. All right. Sorry about that. Let me try again.
Let me know when it's loaded. I'll put it up for you.
Sounds good. I don't think it's liking a video.
Oh, you got a video first?
Yeah.
Try to put it on a regular one and try it again.
Yeah. Okay. There we go. Share. Can you see my screen?
Yeah, we're up.
Oh, beautiful. All right. Thank you, guys. Sorry about the technical difficulties. So I am working on designing a conical shaped Tesla coil. And so I was reviewing some of Tesla's original patents, and I found this is his original cone Tesla coil. And it's funny how he used to call them Tesla coils. He would name them that. And when he created this conical design, he said that it boosted him up into higher voltages, up to 100 megavolts. So 100 million volts, that's totally insane, especially in the day of no transistors or solid state. And so if you see this skinny little wire here, this is the primary. And here we can see it's sort of a cone with the top cut off. The reason why the top's cut off is because as you get pointier and pointier, you start losing energy. In fact, when I design mine, I think I'm going to design it upside down, and I'll explain for that when I have the presentation. But I thought you guys would like to see this. It's pretty cool. Let's see. So here you have my cone. I set up an upside down brace, and I'll have this wound shortly. I spent a lot of time on my pyramid coil, which I'll be sharing with you guys here in a little bit. So if you dig up the information on Tesla's conical or cone-shaped coils, You can actually go to sites. PBS actually has a special on his experiments, Tesla coils, or Tesla's experiments. And so you see it's interesting. These two are having outblasts of plasma and pretty cool stuff. This is another one of his coils. And here he preferred to turn the coil on its side. And what he's done here is the primary of the coil, instead of being on the outside, he puts the primary on the inside. And he liked to put his coils horizontal. And here you can see the plasma discharge. But I thought this was interesting. When I was reading through his patents, I also noticed that he would stick rods about the same diameter of the inside of the secondary coil. And with the iron rods, it created a lot of heat, but he did like the other characteristics because it would have more power, magnifying the magnetic fields. But in the end, he eventually settled on the air core because the center rod would get too hot. And running across another interesting patent, this reminded me of what Nathan has been spearheading. And so here Tesla says, system of electric lighting. And then as you see his setup here, there's only one wire per light. And so this was his one wire technology that he had at the time. And I've been a big Tesla lover since I was a kid. I've read almost every biography that's been written about him. And I don't remember him mentioning this one wire power. So here he is in 1891, and now to take the mantle, if you will, from Tesla, Nathan is carrying on his one wire experiments, which are just interesting. So if you remember, I was trying to make mica capacitors with bismuth. Well, the melting temperature of bismuth is over 500 degrees Fahrenheit. And so that was just too hot for me to work with. And then I found this, it's called fusible alloy. And this is 50-60% bismuth. And then it's mixed with some other alloys. And this melting temperature is only 140 degrees. So talk about easy melting. So I'm looking to now use this to get to my bismuth capacitors with mica. So I thought I'd share. Anytime you want a metal experiment and don't want to have to deal with a blowtorch, this stuff is the bomb. I was shopping at a thrift store and I come across this 3-pound piece of crystal. And so my hope is to wind it as a Tesla coil. And since it has that nice, beautiful hole in the center, I'll be putting some rods down the center and hopefully perform some of the same experiments as Nathan. It was $3, so not a bad buy. I found these these graphites. Excuse me. A sip of water here. These graphite are conductors here to the moving of the rotor. And I'm going to take this graphite and use some oxidized metals to create diodes. And so I thought I mentioned it in my prior video. I'm mentioning again that I'm going to have a design here soon. And really my goal is if I can design my own coil, my own diodes, my own capacitors, I'm slowly chipping away to become basically not needing most of the materials for my Tesla coils. And it feels like I'm getting kind of closer to closer to Tesla when he was working in the 1890s and he had to make his own items. So this is just a side thing I'm doing, and so I thought I'd share. So I put my miscellaneous assortment in the front. So you're going to get the miscellaneous, and then we'll get into some of my coils. Here I store all kinds of different sizes tie strips. And the reason is I use them every day. I don't know of a day where I'm not tying something off. So this has been a real help for me to just have sorted on my desk. Here's another thing. Awesome. I use clear tape maybe 10 times a day. And so I bought this heavy duty one. And you need wires to do what you want them to do, things to stay where you want them to stay, but you want it to be able to pull it off later. This tape is invaluable. I go through rolls of it a month because I use it everywhere. It's great stuff. So here I found some heat sinks, and as I put them together, I was able to get 2 nanofarads. So this is an air capacitor. So I'm going to take this to the next level because that will give me a 2000 picofarad vary capacitor when the most powerful vary capacitor is only 1000 picofarads. So I'll be having fun with this one as well. I want it to be adjustable, but I also share that. Oh, and where do I get these? These are expensive if you want to buy them. But if you go to thrift stores and you buy old radio receivers, you'll get at least 6, maybe even up to 10 of these kinds of heat sinks. And then if you want to come and use this kind of idea of an air capacitor that's adjustable, that would be the inexpensive route to take. So I'm using a new type of wire. Its name is called Solderon. It's this green wire below. I just happened to print a green coil form here to coil. It was just a coincidence. But this wire called Solderon, instead of having to apply fire to it because the enamel is hard to get off of, and then you have to scrape it or use a sandpaper, not for this wire. If you take your soldering iron out and just run it across the wire, you're ready to solder and use it. And so they put something in the enamel coating that the soldering iron removes. And this wire costs the same as other wires, so I don't really see a downside other than I'm going to spend a lot less time cleaning my wires to make connections. There it is again. And solderon, it's kind of a catchy term that you can't forget, so that's the name. And so I purchased some Litz wire. And if people aren't familiar with Litz wire, this is about 1 millimeter in diameter. This looks just like a simple wire. But when you pull out the strands, this is 540 separate pieces of magnet wire. So not one single strand here is touching electrically the other strand. And what this kind of Litz wire does for you, and I've used it in this case, is if you have high frequency, it only runs on the exterior of a wire. And so if you were just using regular braided wire, you would just have it running on the exterior of the braided wire. But if you use an enamel coating on each strand and they're not touching each other, then that gives 540 paths in this example of running on the skin of the wire, and that ekes out a lot more efficiencies. You're going to get higher power transfers, and so it's all around a good thing. The new microwaves that I've been taking apart, if you have purchased one recently, it'll say inverter technology on the front of it. Well, that inverter technology is they've taken out the big clunky MOT, they call it, right? The microwave oven transformer. And they replaced it with this really space age looking transformer that has all these different kinds of Litz wire wound in it. So if you're looking for some good Litz wire, you can find one of these newer inverter style microwaves at a thrift store and pick it up for $20. And you'll have that Frankenstein capacitor with all the Litz wire. All right, so another tip here. I use a Sharpie. I write on everything. Write on everything everywhere with a Sharpie. I see it there. I misspelled pyramid. The reason for that is it comes off with alcohol. So I'm very forgetful. I have ADHD, so I have a short attention span. So I'm writing on everything and then I'm taping everything. It just seems to be the best tools of the trade. I give these tips because I wish people would have explained these things to me when I started the hobby. My friend, he's 92 years old. He calls me little brother, and he gave me this Van de Graaff machine from, I think it's late 1940s, 1950s, and it's huge. And what I'm hoping to, once I get it working, I sort of got it working, but something then broke. But when it's working, it can throw 1.5 to 2 foot streamers. And that's a lot of static electricity. And I'm looking to use this in creating some of my Electrets. So when this thing's running, I'll get some good video of it, but I thought I'd introduce you. It's probably about 3.5 feet tall. And this thing's about 2 feet wide, or 2 feet in diameter. So this thing's big, very big. And I picked up this book, going through a lot of books on electrostatics. This is the best one for the non-electrical engineer, for the non-scientist. And he'll teach you how to build one, which is pretty cool. So I thought I'd mention that as well as I'm getting into the world of Electrets. Electrets, everything is static electricity, high voltage DC, statics, electrostatics. All right, so now I embark on building a golden ratio pyramid. This is what it looks like in my slicer. I'm getting ready to print it. I used a really cool filament. It's called iridium gold. So it has a sort of gold metallic feel to it. And I only buy Bamboo Labs filament. This is a PLA, interestingly. So PLA is really easy to work with. It just has an aesthetic quality that I wanted. So here it is printed. And came out looking like this, no extra plastic, nothing. So it was a great print. Here's how I winded it. I have the pyramid on one record player turntable. I have the wire on another record player turntable. And over to the right, I'm watching a YouTube video. So it's patient work. I enjoy it. And the exciting part is to pump it with electricity. So here's what it looks like. As you can see, every time I fill up with wire, then I have to change to the next level, fill it up with wire and work my way up. Because this is a triangle here, I'm getting 225 turns of wire in this lower section grooves. And then as I get into the middle, it's around 105 turns of wire. And then literally it goes from 105 in the middle all the way to 1 up here. So yeah, I kind of didn't think about the top here. I think the grooves should have been better, but I was concerned about making it look nice, and it does look nice. As I'm winding, I'll just do a dab of oh boy, super glue. I would put a dab of super glue, and after that, I'd blow it real quick. Just give it a big burst of wind here. And what happens is it clears the super glue away from the sides or blows it thin. That way it doesn't clump anywhere. But this then stops my windings from just springing out and turning into a rat's nest. So, and I got this really good point from Ian. I had done it in the past, but Ian, he's really sharp, keeps a sharp eye, and when we message each other, he keeps me on track. So, all right. So next thing we need is a form to put the pyramid into, so we can fill it up with 2-part epoxy. Okay, so there I'm placing it into the form. I'm taping off the loose wires. There's a wire at the bottom of a pyramid, and there's a wire coming from the top. I'll drill a little hole to let the little wire out, and I'll use a hot glue to seal it. That way the epoxy doesn't leak out, only the wire sticks out. Here we go. Fits perfectly. So here it is in my vacuum chamber. It barely fit. And this was unfortunate because normally I'll have a cup that has 2-part epoxy next to it, and I will remove bubbles from it 2 or 3 times, and then I'll pour it in here, and then I'll run the vacuum chamber a couple more times to get the finest bubbles that are still stuck in here. I couldn't do that. I had to pour it directly in my mold, and then I had to get the bubbles out that way. And I could already tell that my form, the light blue form, started to shrink a little bit. So I could tell that this was turning into a little bit of a disaster. But, you know, I can't look back. I got to get this thing working. So this is what it looked like before I put it in. Look at how pretty it is. Kind of rub it in, because when you see it in the epoxy, it won't look this pretty. So, okay, this side looks pretty, the bottom. So it has that sort of mirror-like sheen. 2-part epoxy is fun to work with. Oh, another video before I added the epoxy all the way to the top. Here, if you look at from the top, there's a stairwell all the way down to doom inside the pyramid. No, it's just wires. Here's another picture, glossy top. So even though I use Vaseline as a release agent, this form was just a hair too small. And because of that, it sort of created a suction. So what I did is I would apply a heat gun, heat the spot up, and then peel it away with my pliers. And it took me 20 minutes, so it wasn't bad. There, I'm almost done. And you can see that I didn't get all the bubbles, which is unfortunate, because if I didn't have the bubbles, it would have looked really great. But I couldn't. I need to make the form about 5% larger. But this is what it looks like. Another picture of it. It looks kind of like a, I don't know, an extra sized candle with this little wire up here. So here's the pyramid. I'm going to make it the secondary of a transformer. At the bottom, I found some red wire at a thrift store, and this was a clear container you use to put, I don't know, like baking things, chocolate chips or something. And I just needed some turns of wire. And how it works is the high voltage AC is going to go through all of these turns and then come out the other end. That's going to create a magnetic field that shoots up through the pyramid. And then that up and down in the pyramid action is then going to induce a high voltage, which should then be coming out the top. That was the theory. And here's my test light. I found resonant frequency, but you'll notice it has no breakout. Not until I do that. So my guess is because it can't push out its own breakthrough, that there's just not enough wire density at the top to sustain the push of the energy into giving us plasma discharges. Because you can see it's got some nice high voltage coming out of it. I mean, that's pretty impressive. But because it sort of has to decrease as it goes up, it seems that it sort of petered out at the end. Here, I'm going to run another test. Okay, it does light a light. Oh, look at that one. This one goes further. It should be having these streamers without this. This is just not going as expected. But, you know, it's the best I can do. It's the first time I tried. Let's see here. Is this another one? Oh, it's a photo. Oh, I see. So when I turn on the power, basically the pyramid looks like this. And then when I turn on the power, for less than a second, it shoots out this plasma discharge. And I'm so excited. I go, yes. And then nothing comes out. So it has it in it for some reason. I can't push it out yet. And I'll have to tell you, I have tuned this thing so well. It should be putting out an output. So maybe it's a pyramid thing. We'll see. I'm printing 2 more pyramids to test. But for now, it's turned it on. And then for a millisecond, that comes up. And then that's it. All right. So Nathan mentioned to talk a little bit about safety. So there are really 2 things you want to watch out for when you're working on electricity. You have to first think about your body as if your arms were wires and your legs are wires. So if your leg, your foot is not grounded, or I'm sorry, is touching on a surface that can be grounded, and then with your arm, you touch something that's electrical, you're going to see a cycle like this. It's going to go right up your foot and right out your arm. So what I do is to disallow these kinds of electrocutions is I have rubber mats in my lab. I also will wear a rubber bottom shoe. And that way then 2 layers of rubber, there's no way electricity is going to come up my leg and out my arm. So this is a way to think about it, a good way to think about it. Another way to think about it is if the electricity comes through one arm and then out your other arm. So in the last picture, it went down from the arm to the heart, down to the leg. Here, it's going from arm to arm. And so if you were to say this in a short way, with one sentence, you would say, don't become part of the circuit. That's it. Don't become part of the circuit. So rubber mats, I mean, if you have a concrete floor, as long as it doesn't have any moisture, that's fine. Or asphalt, as long as it's not wet, it's fine. I just prefer buying these large sheets of thin plastic. That way I don't have to worry that I could be grounded somewhere. And then when it comes to working with electronics, notice this is a metal surface. I don't have metal surfaces. All my desks, all my carts, all my work areas, they're all wood. And that's on purpose. My wife did offer a really nice rolling cart, but it was made out of metal and glass. And I said, yeah, I can't. Not with high voltage. It'll find a way to get me. So that's smart. And so when you're working with one hand, if this guy was working with one hand, then he would not be electrocuted because there would only be one path here to stop, so it won't go anywhere. But if you provide a path for both hands, then it's going to go through your heart. I wanted to show you where the dangerous parts are on a ZVS. And I want to say first, warning, this circuit can kill, okay? So you want to, it's basically like basic firearm training. When they hand you a gun, let's say to train you, the first thing to remember is treat a gun as it's always loaded. Well, that is sort of synonymous here. Always treat a circuit as if it was loaded. When I say loaded, I mean loaded with electricity. It's running a load. It has electricity in it. Always assume it has electricity in it, because then you will be looking at it with the right sense of what's the word, tension. and respect it and say, okay, I need to get my gloves on. I need to get my insulated screwdriver, and I can start taking off these screws. And once I disconnect it over here on the left from power, and I don't have any charge capacitors, then everything is safe. So stopping the power, the input power, can make the circuit safe. But there's one more thing to look at, and that is capacitors. These two capacitors can hold up to 630 volts each. And actually, it's 1200 volts DC, 630 volts AC. So these could be charged up to 1200 volts each. And if you were to touch them with your hand, it would be a serious shock. It wouldn't kill you, but it would do damage to your hand. If you had touched one end of the capacitor with one hand and another hand with the capacitor in the other hand, then it would go through your heart, and that would be very dangerous. So not only do you want to secure the power, you always want to be watching out for your capacitors, because they can still be holding charge. And I've had capacitors hold a charge for years. So these little boogers can be dangerous. So now we have the ZVS circuit. We hook up our little DC 30 volts input. Here we connect it to the coil 1 of the Tesla coil. And the voltages output are 300 volts DC to, oh my goodness, it's not DC, it's AC, sorry. 300 volts AC to 900 volts AC will come out of here. And so, yeah, oh, it's nice little 30 volts DC over here. Yes, it gets amplified into AC, and amplified AC is dangerous. Anything over 120 volts, which is in our outlets, is considered high voltage. So that would be the category here. But this voltage also has a frequency, and they roughly run between 25 kilohertz to 800 kilohertz. The best I've ever done on a ZVS was 795 kilohertz, not quite to 800. So they like this range here to work in. There's a positive here where when you get up to 150, 200 kilohertz, then what happens is something is called the skin effect happens. And so let's say you touch this circuit and it's 200 kilohertz. Instead of the electricity going through your arm and through your heart and back through the other wire, it would ride on your skin. It would just ride on the surface, and you would not have any, you wouldn't have any damage. So that's the good thing about working with high frequencies, is that dangerous voltages like 300 or 900 volts, they're a lot less dangerous if you're up in the 150, 200 kilohertz or higher range. And so I mentioned that here. Again, if you don't have the training and the experience, this is not a safe circuit. I'd be glad to help people with this circuit to ensure that it's safe. Take a few precautions, but right now, if you don't have some background in learning, or if you haven't just built 100 of these and figured them out, then I don't recommend doing it alone. So here's our capacitors that I pulled out of my capacitor drawer. This is an audio capacitor. This is ZVS. This is also another ZVS, and you'll see these all around in high voltage Tesla coil circuits. The metal one here is from a transformer, and notice I have an alligator clip on this transformer from a microwave oven. That's because these can kill you. You literally can die from touching these microwave capacitors. Now, there is built inside of them a 1 mega ohm resistor or a 10 mega ohm resistor, and they call that a bleed resistor because what it does is if it's holding a charge, let's say 2,000 volts, and you're not using it, it's going to slowly bleed out through that bleed resistor and discharge the capacitor. But they can fail, so you always treat these capacitors as if they don't have them and that they're always charged. So this is the average size capacitor. These are smaller capacitors, but don't let size fool you, okay? This thing can hold 20,000 volts, this blue ceramic, and this one can hold 1,000 volts, and yet this is smaller than your pinky nail, so size doesn't always matter. It's the values. Another thing I have for safety is I have a fire extinguisher. Any kind of job where I'm not familiar with and I'm going to power it up, I'll just have this close by. This is another thing that I feel like if you're in an enclosed space, I live in the frozen north, so it's very cold here, so I can't keep the windows open. So I picked up this air device. It checks the purity of the air, and I set it up to look for ozone. And it helps a lot because I'll smell ozone and I'll look at the meter and it doesn't look very high, or I'll get used to smelling it. I don't smell it anymore, but it'll start to show this yellow over here, the slight. And that's where I go, I'm out of here. Because if I get into moderate, it's going to start hurting my lungs. So this is a cool little gadget. It's helping me in these enclosed spaces. So here is one thing that I do every time I use my meter. And that is I put it on the tone here, and then I connect the leads. And if I get the tone, then I disconnect the leads and then I connect it to the alligator clip that I'm going to use. So I'm verifying two things. I'm verifying the connections to the fluke meter. And there you go, C0. And then I'm pulling up my jumper and I'm going to check my jumper and it should also be 0 ohms. I do this because I don't know how many projects I've worked on, and I'm using 10 alligator clips, and one of them's faulty, and I think it's working, and then I pull my hair out to try to find it. So I have this standard practice. It's what we were taught in the Navy. You always check your meter. You never assume the leads are working. That way, when you're working with it, then you're getting the correct readings, and getting the correct readings when you have dangerous electronics, that's very important to have. So here we have the Variac. This provides AC to your projects. There's a top view. It says 130 volts, even though my walls are around 115 volts. So it'll still step it up higher than the input voltage. You can see that the knob turns here to give you the different voltages. But one thing that can be very dangerous is when you leave the coil in here, these are exposed wires. So this would be like plugging this plug into your wall and then leaving these open wires. You wouldn't do that. Nobody would do that. Well, the same principle applies for this device here, because if this is dialed up even to 90 volts and it's still plugged in with these open wires, you or someone else could touch them and get a very, very bad jolt. It would not feel nice. It's 60 hertz, so it would go right through you. It would not go outside on the skin effect. So I always pull this cable out. That way nothing's plugged in. And I'm glad they painted it red, because you need to know where it's at, what it's connected to, because this machine can kill you. Here's how I pull out my high voltage capacitors. I first connect with one hand a jumper that I tested, and the other hand I have a glove, and there you go. Now I know that that's not going to shock me. I have pulled stuff out of my capacitor drawers and have bit me more than once, so I don't play anymore. I always have alligator clips, put them on, and then I pull the capacitor out and get it to work. So this is the Slayer exciter circuit that you're allowed to dial in sort of the discharge and frequency with that little knob on the left. I know someone had asked me last week if I could show this. If you go and use the plumbing that's under your sink, you can buy this at Home Depot for $3. It's a very small plumbing pipe, and you can buy then the oversized PVC pipe over it to use as a secondary. And then this is wire from an old plugged-in device that I just cut off, and a capacitor that I found in a stereo, this cooling fan I found in a TV set, and then you're going to have the resistor, and you have this 5K potentiometer, and voila, you have a functioning Slayer exciter Tesla coil. It doesn't keep as cool as Nathan's. With this little fan, though, you can run it up to 30 seconds, maybe a minute at a time before you have to turn it off. Here's the diagram. If anybody wants me to send this to them or email them this diagram, I'd be glad to share it. I know I shared it last week, so I think I didn't think this was it. I'm sorry, 1 second. Oh, wow. That's interesting. Let's see. Did I get through? Oh, I did. Wow. Well, thank you guys. Thank you guys for staying along with me for some drive material. I hope you got something useful out of it.
Right on, Shawn. Good job, buddy.
Thank you. Appreciate it.
Oh, sorry, my mic was muted. Great work.
Yeah, we'll put this on your channel, Shawn, so that people will have that diagram anytime they want to look at it.
Oh, that sounds great. And I'm sorry the pyramid was a dud, but I think it has some potential still.
Well, I think so too. So hold on. I just want to give everybody, this is Shawn Calderon's new YouTube channel. He just set it up. So make sure you guys subscribe. He's going to have some cool Tesla coil stuff coming out on there and his capacitors and such. It'll be really awesome.
Thank you.
Then, Shawn, I started some comments. So basically, if you go up to the top on your comment section, it says starred.
Yes.
Go ahead and click that.
Okay.
And there'll be some questions in there for you.
Oh, awesome. Awesome.
So if anybody is watching who's really interested in Tesla coils, Shawn is the channel to go to. He's got some really unique stuff that you won't find anywhere else. Just flat out. Some really amazing systems.
Thank you so much. This means so much, guys. You guys are wonderful. I don't know what to say.
Well, he just started it, so guys, give him a little time, but he's going to have a lot of stuff on there. When I get him in the groove of getting stuff on there, man, it'll be awesome.
Yeah, Nathan's my YouTube big brother, so he's going to take me under his wing, and I really appreciate it. So that's awesome. And I thank you guys for these questions. So Vortex says maybe a ball on top, Nathan.
Hold on a minute. Yeah, you can click on it, by the way. Just click on it. On the comment.
The question.
Yeah, click on it.
Okay. Yep. I clicked on it.
Okay. It should let you put it right on the screen. As soon as you.
Oh,
it should have a little plus there. You see it?
Sorry, guys. I'm still learning. I don't see a plus.
Okay, I'll do it for you then. It puts it on the screen for you.
Oh,
so
it did
everybody can. Yeah, so everybody can see the comment.
Awesome.
So this is when we're talking about the actual pyramid Tesla coil. We were discussing taking off the top inch because you had just shown the cone Tesla coils where he couldn't put the wire all the way up. So cutting off the top, maybe putting a round ball at the top or something in order for the load.
That's interesting. Yeah. I was trying to think how I was going to do that. So nice job, Vortex. All right. We got 3D Havoc. Should the wire be ran counterclockwise instead of clockwise? So it doesn't matter how you wind it. The only thing that matters is all the coils are wound in the same direction. And if they're not wound in the same direction, then you're going to get a significant power loss. And so if you're winding, like I wound the pyramid clockwise, and then I wound that bright red wire clockwise that was under it, and it worked. That's why you're able to see it work, but not up to my standards yet. I hope that answers your question.
Yeah. Ben had a question.
Sure.
What's the best way to discharge a high voltage capacitor?
If there is any, I don't know if there's a safe way to do it.
Yeah, so people do it the hillbilly way with like a screwdriver, and they'll touch it across the prongs. What I'll do is I'll put on a glove and I'll put alligator clip on them. Now, when you alligator clip one side, you won't really have a reaction. But when you alligator clip the other side, you're going to hear a crack sound. You're going to see sparks, and it's going to probably cause you to drop it. But that's okay. You did what was good. And if it falls on the ground, just carefully pick up the wire again and make sure that it's shorted out, just like I showed you. Mm-hmm. I've taken apart equipment built in 1992 stereo receiver, and there was a couple charged capacitors. I couldn't believe it. Now they weren't fully charged, but treat them as they're all charged if you're digging into electronics or building things.
Right. No, that's a good methodology, a good way of going into it. Just treat them like they always have a charge. And again, ladies and gentlemen, Shawn says, drop it like it's hot.
Nice.
Oh my goodness.
So you may have considered that pyramid of failure, but everybody liked the arc in it. The fact that it lit up was cool.
Yeah, the fact that it didn't produce an arc until you got something close to it, that was actually really cool. I thought that was interesting.
Oh, good. You weren't bedazzled by a fountain of high voltage.
No, it seemed like maybe a more stable coil. I don't know.
Yeah.
Vortex brings up a good point. So when you have rubber mats and I'll add lower humidities, then you can easily build a static charge. And then what you'll do is you'll pick up your MOSFET and discharge. And that little gate on the MOSFET's so sensitive, you'll blow out that MOSFET and not even know it. So that's why they have the wrist straps, where you're being grounded as you move across your rubber floor, and you're not building up a charge to zap your stuff. So yeah, good point, Vortex. Yeah.
Oh, I've fried a graphics card like that. Just, socks on the carpet, building up static discharge, little tiny shock on the, graphics card, and bam, it's fried.
Isn't that horrible? It's so horrible. Yeah. Something so small. All right. Mike does. Let's see. Yeah, man, I'm always ready for a zap. So Mike likes to be shocked. Well,
I don't think that's what he meant. I think he was bracing for it.
Oh, he was?
I don't think he likes it at all.
Oh. That's funny. That's funny.
I think he did mention a method that he had to brace for it, especially like he had his toes in the ground or something.
Oh, that's funny. That's funny. All
That's
right,
awesome.
Let's see. What about add a miniature ice machine to cool the temperature down and redirect electric leakage into a battery charge? So the only electricity discharge was the top. You could see that it was melting away the top of the pyramid. It was melting the epoxy. And is he asking to cool that down? cool the temperature down, and redirect the electricity. So yeah, if I was able to solder a wire to the top of the pyramid, then it wouldn't get hot. It would be fine if it was a thick enough wire. So that would be the way to do it. The reason why I don't have a wire on the top is because the epoxy shrinks at a different rate, and it snapped my little wire on the top. So I couldn't find the water on the top. So you know what I did was I treated it like it was going to work. I hooked it up to ground, and I found resonant frequency, and you saw I found that little wire, thinner than a hair. So now I just have to dig it out. But I like the sphere question. Take off a little bit off the top and put a sphere there. I really like that.
Yeah. Sorry, I'm reading the comments. Yes, that would be awesome.
Yeah.
Actually, I think what everybody's thinking probably in the back of their minds is if you just put a little bit thicker of a top on it and cut off the top a little bit, then can you put another, say, pyramid shape up there of metal? You know what I mean? Would it act as an antenna or anything, or would you get any effect out of it? I think that would be interesting.
Yeah, very interesting. That is a good idea, and I'll have to golden ratio it just like this one, so they're matched. But I can do that. See if I can use it as a transmitter.
It'd be interesting to see, and I know this would be extremely difficult, but instead of just 4 corners, make it 8, so the other 4 inside, just like the Great Pyramid, just slightly bent inside.
So it's an octagon on the bottom?
No. Do you know the Great Pyramid? It's not 4 sides; it's 8. So in the insides of it, it's pulled in just a little bit. Where you think they're straight on the outside, in the center of that, they're pulled in just a hair.
Oh, that makes sense.
So it would just be interesting for the geometry of it to see what it would look like in voltage when you do it.
Yeah, that is interesting. I'll look that up.
Hi, Lulu.
You missed all the fun stuff, Lulu.
Hey, Lulu.
Let's see.
Any more questions?
I'm looking through them right now, Shawn. Feel free if you see any to answer them.
Okay.
Here we go.
So I've done that before, interacting with a coil clockwise with another counterclockwise, yet they're resonating at the same frequency. All I've noticed is power loss. That's it. It's a degraded power. But I haven't spent a whole lot of time on maybe other things you can derive from it. But as a general rule, I always hook it up wrong. And it gives little power, and then I'll hook it up right, and then it has the maximum output power. And it has to do with radians and gradients, and I have no idea what those mean, but if you put a counterclockwise on a counterclockwise, then you have the right gradient. So yeah, it's a good question. Yeah, if you can. There we go. Oh, yeah. Be careful when I work with static charges. Yeah, and then fill up your gas tank at the gas station. Yeah.
Stay away from that.
Yes.
I had the static charge one time, took out everything on the top of my bench. Just, it gets in the melamine on the top of my bench, and it'll ride across the whole top of it and blow any circuit out. Any MOSFET on there is fried.
Wow. So what do you guys think about inviting Vortex to share his latest work?
Absolutely. That'd be awesome.
What do you say, Vortex? I'm not getting any comments. I'm gonna grab my
He's
iPad.
so excited. He doesn't know what to say.
Huh.
That means a yes.
I hope so. He
How
has
the
some really
next-
cool comments.
This guy's a great, brilliant guy who could show us some awesome stuff.
He's still getting over strep. Oh, that sucks, man.
I'll
I
vouch
hope you
for
get
him.
better.
Oh, strep's the worst.
Yeah. Hope you get over that soon.
Yeah.
He said, but when he's done and he feels better, it's a good idea.
Awesome.
There we go. Yeah.
Yeah. I'll keep a bug in his ear.
There you go. Let me know and we'll set it up as soon as he's ready. Absolutely.
Sounds good. I'm just now finding the comments.
Okay, he said, see my comment about the skin effect. I'll look for the comment, but you want to talk about the skin effect? Let me look for it.
Sure.
He's got resistor between two posts. Does it interfere with the nerves at high frequency? I'm going to say yes. I know most people don't think it does, but it does. Here's the skin effect. Okay. Watch out the way you say skin effect. It doesn't apply to a human body because it doesn't create a magnetic field and push it inside.
Yeah. So the skin effect is a term that's used for electricity running on the skin of a conductor. Has nothing to do with human skin. Just people sort of put that together. But it also will stay on the outside or the skin of anything else it touches. So since and I've tried this, you shouldn't try this at home, but I've tried at 200 kilohertz, and yeah, you feel it, but it's on the, you can tell it's on the surface of your skin. It is not going inside, because I've also been shocked inside, going through my body many times. And then when I was in the Navy, we used to have these wired phones, and I was the phone guy. So I get on the pier and I'm in Hawaii and it's raining, and I have to hook these little lugs from these wires connected to the ship so we have telephone services. Well, it's 30 volts when you're hooking them up, but if someone calls you on the phone, it's 90 volts. This is AC. And so I'm working out there, and I get 90 volts, and I'm screaming because that will not be fun.
No.
And my captain would go, "Hey, what's going on?" And I'd scream again. And so my lieutenant, he's responsible for me. He's running out, and he's saying, "What are you doing?" And I tell him I'm hooking up these terminals so we have the telephone. Well, stop screaming.
Stop screaming. Stop calling people. Yeah.
And so he said, "You have to wear gloves for this." I said, "Well, I can't." So he sent somebody to get the gloves. They're elbow high gloves.
Oh,
the
wow.
rubber's so thick that I can't make a fist. And I had to take these little terminals and I slipped them off without them knowing it, hooked it up without screams, and called it a day. But that's the electricity that'll run through you. So yeah, the skin effect is alive and well.
Oh man, that's funny. That'd be terrible. Have my wife in there. I'd never get a moment's peace. I'd be shocked every 2 seconds. She never puts that phone down.
That's funny. All right. So someone's asking what the golden ratio is in dimensions. I just Googled it. A friend, Brian Brum, he's a CAD expert. So sorry I can't give you a better answer than that. Let's see.
Oh, keep watching the video. Take a small DC ionizer, run it through yourself. Safely do that same with hot. You can't do anything safely with hot energy, to be honest with you, ever. It always gets you. Always. There's no games with that. It always does.
Yeah.
But that one video was funny. Shawn sent me that Tesla coil, a little mini Tesla coil thing, and zapped my face with it. He had a good time laughing that day. Yeah, I don't know what they were trying to achieve with that, except for shocking the living daylights out of somebody, but it definitely did that.
It's supposed to get blemishes off your face. That's what they promote.
No, it was adding them.
It hurts.
Yeah, I was adding red marks all over my face is what it was doing.
So if you read the instruction manual, I'm sure it'll just say might cause minor discomfort.
Yeah, minor. That
you're touching your face with a taser. Minor.
Yeah, that's what it is. Don't worry about the taser on your face. You're all right. You use the comb feature for your hair too. Yeah, that was a good one.
Yeah.
Good thing I don't have long hair. That would have been bad.
Vors said, want to send a link to join live, Nathan or Ben?
There's talk of people using a microwave transformer to create that Lichtenberg art. Oh, no. Dangerous.
Hold on. Mr. L said he had, Vortex said he had strep, right?
Yes.
Well, send him a link in case he did want to come on. That's what I think what he said. Or maybe it's for a later time. I'm not sure which.
Maybe. Yeah, I wasn't sure, but I was just literally just about to ask him a follow-up question if that was regarding now or later.
Yeah,
Not
Shawn.
Andy.
He can be brief, okay. So he'll come on. Absolutely.
Yeah, totally.
Shawn, you want to send it to him?
Send him the live stream.
Yeah. Just copy it off of your Facebook and send it to him in the email or to his Facebook.
Yeah, we do that. Let me do that.
Yeah, he said today. Well, we'll be seeing him here in a few minutes then. That'd be awesome.
And I'm so excited because I know a little bit what he's going to do. I think you guys are going to be excited too.
Oh, yeah. I think so too. That's going to be awesome.
Yeah, let me find him. He's changed his name so many times. I'm just razzing him.
Got to give him a little bit.
There you go.
All right. Well, you look that up and take care of that, Shawn. I'm going to talk to Ben here. Ben, you have any updates or anything going on?
Yeah, I got a few updates on the coil. I ran a couple of tests with the 40-watt LED panel. It is the results. We talked earlier, and I was trying to figure out because I have the raw data, and I have the results with the coil and without the coil. The problem is without the coil, it automatically defaults to 100% brightness. With the coil, it kind of dims to about 3.3% brightness. So I had to work out the math. I think I have that worked out. I'm going to give you guys all the results, including, the math and everything, to see if anybody in chat has a follow-up question or if they maybe see an error with the math or something like that. But I'm just going to give you the raw data and what I came to the conclusion just recently. So with that said, let's jump into the first video, just a short video demonstrating the lightning thief on the 40-watt LED panel.
Okay.
Right, so we have the lightning thief running this 32-watt LED panel. It's actually a 40-watt panel, and it consumes approximately 38.6 watts from the wall, according to the Wattman that I have, which is pretty impressive. Off of this 12-volt battery. Let's take a look at the voltage drain. It's been running for about 30 minutes.
and it started at 12.34. Might have been 12.35. But, we're gonna keep an eye on this, see what the rate of drainage is, the rate of energy consumption. You can see, let's disconnect this real quick. So the Lightning Thief works.
Nice.
It's inducing this wirelessly, so it works.
Yeah, as you can see, when you disconnect the load, that protection neon bulb is that neon bulb is there as protection for the transistor on the circuit. But it's just it mostly serves as an indicator that the system is working and in resonance. You can also get indicators by wireless induction, like if you have a secondary pickup coil. Doesn't even necessarily have to be a Rodin coil or a ABA coil. Just any kind of pickup coil nearby the vortex should be able to induce that energy wirelessly just with the system in resonance, which is pretty cool. And so we ran the, here, let me pull up the graph. Put that down. Okay, share screen. All right. So here we have the first graph that I have. It doesn't have all the data points on it. I'll show you the final graph in a second. But since I got the LED panel working Saturday, I was testing it on the Lightning Thief to see how long it would last compared to just powering the light with an inverter. Actually, I'll show you that now. This is the inverter that I was using, just a standard car DC to 120 volt AC inverter. I cut the end off and I just hooked it up to the battery, and I plugged the Wattman in here so I knew exactly how much the LED panel was consuming. And you can see with the inverter, you can even see it was only consuming 37.4 watts approximately instead of the full 38.6. And this makes sense because there's going to be a little bit of loss with the inverter. I think the most efficient inverters are around like 90%. So they still have about a 10% loss of efficiency, which makes sense because the inverters are they're very hot. You know, they have venting and cooling for a reason. I've even had one that caught on fire, so they're not very safe either sometimes. Oh, hey, what's up? We got Vor in the house. How you doing, man?
Hey, can you guys hear me?
Yeah.
I definitely was not planning on getting on today, but yeah, I'm here with you guys. Just wanted to say hi, and I've been in the background, you know, been sick, but I'm here.
Yeah, we saw you change your name on there.
Yeah. Miscellaneous, I guess people were having difficulty pronouncing it, so I
That's
switched
me.
to Vortex.
Love the beard.
My camera, my webcam, I didn't charge it up, so I'm trying to wing it from the phone and the computer at the same time. There's a little bit of a delay, but we'll get through it.
It happens with the phone. I've had it happen with my phone too. Yeah, it sucks.
Yeah, the phone's not the best.
So, to continue where I was, where I left off, we ran the panel. When plugged into the wall, the panel consumes approximately 38 watts fully bright. The Lightning Thief powers it very dimly at about 3.3%. Now, this was a challenge for me in comparing the two results because I had to adjust the results without the coil, the results with the inverter, to reduce that from 100% to 3.3%, which with the wattage consumption we can actually do. I just need to make sure the math is correct. So I can't say indefinitely what the results are, but they do look very promising if the math is correct. It powers it at 3.3% brightness of its maximum brightness, right? In retrospect, that I don't think that's closer to 20. It's probably about 3.3%. And I believe to be fully tuned, we must lower this slightly until the duty cycle. We must lower the load. So from like 40 watts to maybe 20 watts, we must adjust the load so that the duty cycle reaches 50 on the output. Right now it's at 60-40, which is an increase from the 95.5 that we've seen with the other load that I had attached to the 12-volt battery, which is very, very significant. So that tells us that we also need to tune the load with the system as well. And by choosing the load carefully, we can increase the efficiency. So let's take a look at the graph real quick that I have. Give me 1 second, it's loading.
I was putting this in the comments how I thought Vortex would be a guy in a bow tie and a dinner jacket, and I didn't know he'd be out in the woods of Alaska. It's amazing.
Everybody's growing their beards out. I gotta keep
That's
up.
right.
If my wife let me, I'd have one.
It's like 90% of the people that present seem like they have beards.
Yeah. All the cool kids have beards.
Trying to
So this is
become Santa Claus this year.
Yeah, well, I got the stomach for it, and it's going almost all the way gray for it.
Nice.
Give me 1 second. I'm trying to pull up the graph real quick. Oh,
Yeah,
there
there's
it is.
Joe's got a beard too, man.
Yeah.
Yeah. I'm the odd man out. Oh, Gerald.
Yeah, Joe doesn't have quite the beard yet. He's got like a goatee going. Ben's got a beard.
Yeah. I'm gonna use that to tell my wife. All my friends have beards.
Why can't I have one?
They're making fun of me.
So this, I don't think this is actually accurate. Let me double check this because one of these lines isn't accurate. Let me check this real quick. Tesla's coil, so that is 80 minutes. Okay, yeah, so that no, that's accurate. But it's because we can't see the cutoff line. The cutoff line is 11.5. So we're cutting the system off at 11.5 volts when the battery reaches that. And it's weird because with the in the other graph that I'll show you in a second, with the cutoff for the battery, like it seems to go, it consumes at a steady rate, the battery, and then it seems to slow down, like it's stabilizing with the coil attached, and it slows down for a while, like at least 24 hours. And then once it reaches, like, I didn't see the exact voltage, but once it reaches like 11.6 or 11.5, it just takes a crap, and it like immediately starts consuming a lot of the battery. What I mean by that is it consumed like almost 1.5 volts, went down to like 9.4 volts in like 30 minutes or something, like ridiculous. It was really crazy. So you want to be careful with the system because it has the ability to drain those batteries really, really well. So without a system in place to stop it at 11.5, we could have that sulfation buildup. Trying to find that other graph for you. I thought I saved it. I might have moved it to a different folder. Let's see. Okay, I can't find the other one. So I'll just give you the results for the first test, which was the battery drained to 11.5 after approximately 60.5 hours. So this is a significant amount of time, but again, it's only about 3.3% brightness. It makes a good night light. Like I can't really get it any brighter at the moment. But when we compare it to our results with the inverter, something interesting happens. let me pull that up. So we know that the system consumes 38 watts. And we know that when I hooked it up to the inverter, it was only consuming about 37.4 of those watts, leading us to believe that the inverter is a slightly inefficient, which makes sense. So what we saw, though, was it lasted 77 minutes. Now, when I did the math, and I could be wrong, but let me show you guys. I'm going to share the screen real quick just because I did this. Let me move this over here. So I did this with ChatGPT and it looks accurate, but I just, I always like to double check with the AI because sometimes it is wrong. So basically, the way that we adjusted it is we took our brightness ratio by taking 3.3 and dividing it by 100, which gives us 0.033, right? And then the step 2 of the equation is we have to adjust the power for test 2. So we do this by taking the total amount of wattage that it's going to consume, 38.4. We times that by 0.033 and we get 1.27 watts, which is the watts that it should be consuming if it was adjusted for 33% rather than its 100%, which is what it was at. So we take the amount of time that it actually ran for, 77 minutes. We times that by 38.4 divided by 1.27 watts, and we get 2,331 minutes, or approximately 38.85 hours, which is very significant because if this math pans out, and again, this is, I'm not good at math, so I'm leaving this up to you guys to help me out here. If this math pans out, then we really have something here.
Nice.
We need Sears, Victor Sears.
Yes, we need Victor Sears on this to help me because I'm at the point where I'm collecting all the data now, but I'm not a mathematician. I'm not, I need help analyzing and organizing the data into something that's actually tangible and something that we can make sense of.
Nice.
It does last a long time, and I have been using the nightlight for my lab. It's, it lasts freaking, 2.5 days, 3 days, something like that. It's crazy.
Yeah, it sounds like you're onto something. It really does.
You're doing a great job, man.
Very good.
Appreciate that. Sometimes it's hard to tell, what the efficiency is, but I think we are really onto something here.
Yeah, agreed. Well, good job there, buddy.
Yeah.
Appreciate
nice work.
that.
Yeah.
Yeah, that's all I had to present today, and we can move on to what Vor's had.
Yeah.
All right, Mr. L.
I can
Vortex.
discuss just a little.
What are you working on?
Well, it's hard with the phone. I can try to so I just got a provisional patent for a method of producing electrets and magnetoelectrets that involves what I called an aggregate and a binder. So with the aggregate, you could take something like diatomaceous earth that's high in silicon dioxide or sand. The sand's not as high in silicon dioxide, and you can shake it. And the opposite table would be something like PVC. The PVC would acquire triboelectrically a negative charge, and the sand, by shaking the sand in a container like this, the sand becomes positive charge. And you could take a geopolymer binder or any binder, hot glue. I just got to try different binders to lock in the charge of the aggregate. And what that will do is give me a much higher charge density, because whenever you use conventional methods, you're just putting charge on one side of the electret and the other side, and it's a bipolar electret. But with this, I can control whether it being monopolar or bipolar, and it gives it the charge density since you're using very small particles and filling the volume of the electret with pre-charged aggregate.
And the charge stays once you lock it in place?
Yes, that's the idea. You know, say just as a geopolymer, sand and geopolymer, let's say like the Great Pyramids, if they did something like this, you know,
Nice.
and they would triboelectrically charge the sand and then do a concrete mixture to lock it in. But, you know, of course, then you could use a high voltage generator. That's what I was working on here. It's just a very simple taser
nice.
module with the pulse width modulator.
Hmm.
And, you know, just by triboelectrically charging it, then using a binder, it should just lock it in. But if you want to make sure, you know, you pre-charge it triboelectrically and then you hit it with a high voltage power supply while it's solidifying.
To keep them pointing the right direction while the binder's working.
Right. And it's best to work on the monopolar because you can either use, say, sand as the positive, and then you could use like crushed PVC for the negative, or Teflon, crushed Teflon powder as the negative. So if you
Uh-huh.
wanted a bipolar electric, you just sandwich those two together. But by doing them each individually, you can control the charge density, you know, and however many poles you want.
So your Electret is it's ingenious to have the many particleized insulators rub against each other with the triboelectric effect, and yet because they're insulators, they can't really discharge the electricity that they're building. And now that they're all charged, you put in some binder with that high voltage to keep things straight. And what are you thinking, like epoxy for a binder?
Yeah, anything hot glue, epoxy, like I got to go and test them individually, you know, for each of the triboelectric series. But, you know, as any home experimenter can easily get involved with this, not needing, you know, because it's kind of difficult to make magnets. But if you could just shake different things in PVC pipes, you know, and charge them up, but you do have to have a respirator because stuff like diatomaceous earth and stuff, and since they're charged particles are going to want to expand and repel from each other. So when you open that cap, it's going to be a bunch of
Oh.
charged particles that you could breathe. So you have to have a respirator. And I do say work outside if you're going to do this because you
Is
don't
it
want.
something that you can smell, or is it something that's not odorless?
Yeah, I mean, you can reach 10,000 volts off of triboelectric methods easily. So as if it goes around 10,000 volts on each of those little charges, it can ionize the air and you would get a
Mm,
smell of ozone and stuff. But that's,
ozone.
you know, that's if you like preheat it to make sure it's completely dry, hit it with
Mm,
UV light, and do several other ways you can optimize the charging.
mm.
But you know, just to get started, just taking different containers and shaking them up, and you know, it's almost like a bartender or something.
Nice.
So can you tell us more about your magneto Electret?
Yeah, it's just basically the field orientation. You know, you can just get permanent magnets, you know, everywhere, and you can just stack an electret, a magnet, electret, and different field orientations to get started. And the weird thing about an electret and a magnet is they actually have a 90-degree force towards each other. So if instead of like two magnets either wanting to attract or repel, if you took an electret and a magnet and brought them close to each other, they actually want to shift like 90 degrees.
That is so cool.
Yeah.
It's the what is it? The electromagnetic and electric charge sort of duo, not duo, but they're perpendicular to each other,
Yes. Yes.
and you can show it with these electrets. That's mind-boggling.
Right. Yeah. And, you know, like Sal Pius, he's saying, you know, for his levitation and a bunch of these guys working on that. Charles Bueller, the guy with NASA working on electrostatics and stuff. Their problem is not being able to get above, say, I think 10 to the negative 8 coulombs of charge. That's the huge benefit of mine because the charge is the capacity and the voltage. Like I said, it can get 10,000 volts, you know, per aggregate, but the capacity is huge because you're using a huge amount of aggregates and you're filling the volume. You're not just charging the surface of a dielectric.
Yeah, you're thoroughly well. You've added all that. What is it? The face, the volume of so each piece of sand, if it laid out flat, it would cover more area than if you were to just charge a piece of something as a whole.
It'd be like the surface
area
of a football field.
Hmm.
Yeah, it would be like they say, graphite and stuff. Just a small amount is like the surface area of a football field. That's what gives you the capacity, is by using the aggregates. I can easily get a column and be able to compete and test their theories, because a column of charge to me should be relatively easy. And since I've been under the weather, I've been wanting to get on it, but at least I've got the provisional published, and I just do that as a matter of record. Honestly, it's just so anybody can look it up. And since I'm the owner of the patent, I give everybody, goodwill, go at it and do it. Like I really don't care.
Oh,
nice.
I can share it.
Absolutely.
Awesome.
Oh, very cool.
That's why I wanted to get it, so that nobody can say that you can't,
Yes.
So I'm
awesome.
I need to do the same thing with my circuit. I need to talk to you about how you went about getting a patent, because Michael and we need to protect that, because make sure it's open source. I don't want anybody closing it down and saying, hey, we're going to sell this and you can't know how it's built.
Right. It's motivated also because it will, if I get to the point of manufacturing, it'll dramatically drop it to the people that aren't experimenting like us. They'll have them readily available at much cheaper prices too.
Yeah.
So
it's a good method.
Let me ask you something, because it sounds curiously familiar to something else. When you look up pillars in like Indian temples and stuff, there was a granite pillar. And when you tap it, it made different sounds than it would normally. Like it was how do I say it? That the electron charge or the charge on it was changed at some point. Kind of like when a lightning strikes a rock, and that rock in that position where it is will make tones that are different than what it normally is. Is it the same type of process?
It could be. The charges, could add in the binding. It's more of like a density kind of thing. Whenever you get different tones like that, it's the tensile force, I think, or so the density would increase, because once you add the binder is going to want to give up some of the charges to compensate. So as long as you do it within a frame that doesn't conduct or is grounded, it will lock in the charge, and you can get higher density and better adhesion. And I was thinking, with that experiment you're doing with the sand in the plastic jar, if you shook the sand in the plastic jar first, like diatomaceous earth would be great. Sand, it's got high silicon dioxide, but diatomaceous earth, if you heat it to make sure there's no humidity and shook it up in that plastic bin, and then tried it dry, and then see what happens when you add the water. And then once you add the water, those charges will neutralize by the water, because there's going to be free hydrogen going on, and you should get much higher light output. Like if you shook charged it, tested it, and then poured the water in there to neutralize the charge, you should be able to get high current and high voltage at the same time.
So crazy.
So I could put it in a shaking machine with it in a cylinder, and then pressurize it a little bit and force the water in at a point when I'm ready, right?
Yes. That's
like a timing circuit.
Right.
What's the best water?
Using two different charged aggregates too. If you added them both at the copper sulfate and a electrolyte, if you added it to them both at the same time while it being in a circuit, it would just push the current through to neutralize it.
Oh.
If you're willing to put the work in to shake it, to make a little short battery like that, you could get away with it, but you have to put the manual labor in to shake it.
Well, it's kind of ironic, because Shawn and I were discussing, I wanted to put sand in the center of my Tesla coil and try it, because I wanted the sand to add heat to it in order to push the distance of my Tesla coil a little further. So if I shook it a little bit, put a charge on it, and then threw it in there,
Yeah.
that
Make
that
sure
might.
there's no water on it if you're going to do that, because then what you're
Oh
looking
yeah,
for
dried
there-
out completely.
Yeah, what
I
you're
put a
looking for
heater
there-
in it for a day and let it
Right.
use the, because I was looking at sand batteries as a heating source, and
Yeah.
then this would fall right in line with it.
And I would also recommend maybe trying like panels at one point instead of rods, just to see, because we're saying that Tesla used panels, and that should increase the surface area, so you should get higher current using panels compared to just 2 wires in there. And you could try using UV light, because UV light will discharge negative charges, photoelectric effect and stuff like that.
Wow.
Yeah, it also ionizes the air, doesn't it?
Hold on 1 second. Sorry.
I'm bringing this back.
Thank you.
This is my fruit, and then I'm gonna have chicken salad and my crisp things.
All right.
Yeah. Oh, I'm sorry.
Hey, so when you hold an Electret in your hand, does it make all the hair on your body stand out?
Yeah, Plasma Channel did a good well, he didn't really show the hair standing up. But yeah, it'll have all the effects as just having, just a highly charged anything,
Yeah.
That's why we grow our beards out.
First line of defense.
It's like
But
the
when the
canary in
charge
the
is
mine.
They're my
You know when they
antenna
carry the
to brains.
Yeah. So you're talking about monopoles. How would you, because if you could have a monopole magnet, you'd get the Nobel Prize.
Well, yeah,
I got one of
magnets.
those.
Magnets. That's the thing, is you can't do it with the magnet, but you can do it with charges.
Right.
Yeah, not a magnet, but electromagnet, right?
Well,
any magnet.
You can cheat and make a monopole magnet using like Hallback arrays.
Yeah, it really is more of a cheat, I think. The way that I do it, it's not. I think it's a pseudo monopole, if anything. I think we're just compressing that one pole to the point we just can't detect it.
Weakening
It's
one
still there
side.
somewhere.
Yeah, the thing I want to try is a conventional electric rod, and seeing if you were to have a magnetic rod and cut it in half, you get 2 identical magnets.
Right.
But I wonder what happens if you just took an electric rod conventionally charged and cut it in half. Does it make a positive and a negative?
Right. I don't know.
So these are things that
That's
it's
the
just
big
now
one.
the cat's getting out of the bag, with the Plasma Channel coming and disclosing that, it's funny because I learned about diatribes about 10 years ago, where you can take a coax cable and heat it up in an oven, and you would soften the insulation and charge the outside of the coax and the inside of the coax oppositely, and it'll just sit there and spark all day. And people would use this to wire antennas, and they'll put Teflon tape on there because Teflon's a great negative.
How would they heat it? How would they heat it? The
They just throw it
coaxial?
in an oven.
Oh,
Nice.
yeah.
Yeah, and it would just literally sit there and spark all day. It's just like having a Van de Graaff or any type of high voltage that just
Interesting.
doesn't have a prime mover or anything.
Right.
That's
interesting.
crazy.
Yeah,
Yeah, I'm gonna have to try it. What temperature was the oven? Do you know?
just enough to. It depends on what the insulation is. You just want enough to melt it. I don't know for sure, but you'd have to look it up which insulator you're using.
And it's the inside insulator, right? That needs to melt.
Yeah, they took the outside insulation completely off,
I see.
and then
Oh, okay.
and then it's just the insulation between the circular conductor on the outside,
Yeah.
and then
That's
you charge it
moving.
oppositely with a high voltage generator when it's soft. But if it's too hot, it would just puncture it, and you lose the whole thing. Once it's punctured, it's done for. So you want it right at the right temperature to where if you get a huge amount of current, you're done. But and that's the conventional electric way. So my way would be different. I could just take copper tubing and put a copper wire down the middle and shake it and then do it my way, and it would do the same thing.
Nice.
So it gives a new meaning to the phrase "shake and bake."
Right. I actually was gonna say bake and shake, but me and Shawn were saying it was the BS method, so we were like, nah. I'm trying to think of a good name. Maybe Electret.
Triboelectric sounds cool.
Yeah, that's cool.
But Electret is what it is. I mean, it's a great word.
Then again, you can use magnets too. So, I mean, I was also thinking of just calling them etherets in the case if you're using an electric and a magnet. It'd be like an etheret because it's the combination of the two.
That's what I'm not getting, because you're still going to get a bipolar magnet. If that makes sense.
Is a true monopole magnet even possible, or do you think it maybe exists only at a microscopic scale?
I said, I can cheat and make one.
Holy grail.
Thought about how to do it with Hallback arrays. I can cheat and make one, but in physics, no. In my opinion. Now that's why Electrets are so cool, is because you can do that, and that's just now the cat getting out of the bag. You know, you can have monopole.
So what is an Electret?
It's okay. Imagine plucking an electron out of an atom and just blowing it up to the size of a basketball.
Okay.
That's an Electret.
It's just okay. No, it's a perfect analogy.
I guess that was easier than we thought, huh?
because the charge field.
Proton, you know, the proton's the same thing. That's why it's monopolar, because you have a proton and you have an electron. And if you spin an electric, like if you spin an electric, you get a magnetic field. So the magnetic field is actually an emergent phenomena from the intrinsic electric charges of atoms.
That makes sense, because electrons have negative charge and a proton has positive charge.
Right. And the neutral. Don't forget about the neutral.
Right,
you know.
right. Yeah, we don't want to forget about him. You don't want to be the third wheel. So come on, guys, you always forget about me. You're neutral.
Wow.
I do think neutral is important, though, when you kind of get further into this. Utilizing neutral and grounding is where you get a little bit more advanced, making earth pumps like Nathan's doing.
Right.
The neutral becomes really important at that point.
So it's like a trifecta aspect, or a holy trinity, as it were.
Absolutely, yes. I call it the Holy Trinity. Yeah.
Nice.
Yeah, what's funny is when you start messing with this stuff, you'll develop a 0-point zone in one of your Tesla coils. When I keep running this stuff and I do the negative, I'll hook a second Tesla coil to it, and in the center of it, I'll hit a 0 point. And the top part's charged, the bottom part's charged, and in the center, there's a 0-point zone. Mm-hmm. It's a real interesting phenomenon that happens in this. That doesn't happen in everything.
That is cool.
And you can get away with that. Yeah, you can get away with that using two capacitors too. In the middle of those capacitors, if you just ran a high voltage, it would be the neutral between the outsides of the capacitors and the two capacitors touching. That would be your neutral that you could utilize. Positive, negative, and neutral would be in the middle of just two capacitors in series.
Oh, interesting.
I got a lot more experiments on the table now.
Huh. Yeah, that makes sense, because you'd have an extra rail there. Huh.
Yeah.
I'm excited.
I'll be probably discussing more about that topic later, but just to get started, look up the triboelectric effect and just use, like in my patent, I showed a tumbler, and Shawn said it reminds me of how your socks come out of the dryer. That's what, that's what you want. Like, imagine, I said to him, I don't know if he saw it, but imagine like 1 million ant socks,
Oh, nice. That's a really good analogy.
And then you're binding it with a geopolymer, hot glue, silicone
Crazy.
caulk, you know,
Yeah,
any binder.
that's a better analogy.
So if I buy a paint shaker and I can stick the cylinder in there and I put sand in it, I could develop it where you get it to shake, and then it would all be one charge. The outside of the cylinder would take on. Go ahead.
That's where the neutral plays a part, because if you just want the sand to be positively charged, I would use like a PVC or a Teflon container and shake it in that. But then you want to ground the outside of the container to actual earth ground, and then the positive will stay on the sand in the aggregate of the container.
Okay. That shouldn't be that hard to put together.
Yeah, and the patent makes a lot more sense. I'm not feeling too good, but I went into some good technical detail in that. I can try to post it in the comments section afterwards.
Right on.
I've read it twice, so I'm getting into it. It's great. It's very nice work.
He wants a sequel now. He's ready for the sequel.
Thank you for working on it, Shawn. It's so awesome that you're working on it. But I feel like Electrets are just that other side of the coin that will take us to the next level with technology. We're just getting into it.
Well, let me ask you, if you can take a ball in the center and just charge it to one point and then put another sphere on the outside of that, wouldn't it have kind of like the same effect where you can now pull the charge in either direction when you want to? So you understand what I'm trying to say? If you want to make a core of something and then make it an electret and then put another sphere around it in whatever material, then wouldn't it induce like a gravity type effect to it?
It would just act like a charged spherical capacitor. Like what I'm trying to get into as a demonstration of what you can do when it comes to monopolar is, if you know about electrostatic generators, if you have a positive and negative pole, you can spin something in the middle just by the potential difference on those. But instead of having to use a high voltage generator, if you just use a positive and negative electret, you could spin a motor just in a mason jar.
It's not going to draw current.
No, it ionizes the air. That's yeah, just like if you used a high voltage generator that didn't output any current just to charge those two posts, you're not really putting current into it. You know what I mean? A very little bit amount, but by using electrets, it's just the air ionization that is going to be doing the work.
Oh, and because they're permanently in a charge state and their lines go out radially from the sphere, that interaction just creates ions, and you can direct then those ions to perform work. Oh, exactly. My goodness. Well,
I'm not claiming perpetual motion, you know what I mean? Because just like magnets don't last forever, electrets don't last forever. So it's not perpetual motion. But it's something to think about.
I like to remind people there's a difference between extra energy or over unity and perpetual motion. Like the two are not one and the same. Not always, at least.
Right.
I'm hooked. I'm
not making any claims.
He's not laying any claims.
There's a lot.
No, you're absolutely right. Magnets run out,
Yeah, but
every 100 years.
If you can induce a spinning charge without the static electric effect and ground the second part on the outside of it, you should be able to still get the charged effect on the outside, but without the electricity. That's why I say gravitation, because then you have exactly what we want in gravity. You have the effect of pulling it in, but you don't have the
creating your own gravitational force.
Right. And it's the charge density. That's why this method's superior to what's out there now, is because you're getting a huge charge density.
There's
more
a lot more
surface.
to this than what you're, you know what I mean? The little
Right.
experiment that you're talking about, there's a lot more to this.
More
More than
surface
meets
Absolutely.
the
area.
eye.
Yeah.
Yeah, I've contemplated a lot of things. I can like literally just use it to pull dew out of the air at night, and atmospheric water generators, filtration, drug delivery
Yes.
systems. It's got a huge amount of applications once you start looking into it.
Oh, yeah, it does. What changes the game? I mean, I'd have to get one in the lab and start spinning it and seeing what's going on. You know what I mean? What kind of
Right.
field it produces on the outside. And then, yeah, because I think cavity, creating it in a cavity would be just a game changer. So,
And
at least that's
remember
my
the
opinion
first
of
video.
it.
The first video we did, we were discussing the Tesla dynamo. Remember that, where I had those jugs and I was spinning electrolytes. So if you
Absolutely.
just had electric discs and spun them, it produces a magnetic field and high voltage. So instead of spinning magnets like in end machines and other homopolar generators, you can spin an electric to get the magnetic field, and you got a magnetic field and high voltage at the same time, just by spinning an electric disc.
Amazing.
Yeah, that's
Amazing.
total game changer.
It's cool stuff.
Is it any motion can it cause a perpendicular magnetic wave?
Like if you had the charged basketball, say, and you threw it, the magnetic field would, the north and south would be parallel to the motion. Yeah, so that the magnetic field line would be a circle around the basketball as it travels forward. But if you spun the basketball, then the north and south poles will be on the top and bottom of the basketball.
So would a moving electret create a magnetic field perpendicular to itself?
Just like moving electrons, it's the same thing, but whatever geometry you use, just think of what an electron. Yeah, it's just a macroscopic electron or proton.
Interesting. I was excited when I heard of it.
Yeah, it's not just balls. Cones would be good to focus the fields and all that stuff. So all the geometries matter.
Yeah. I'm just figuring out how to melt the materials and then put them under great high voltage strain just to learn how they react. I do like your...
You don't have to melt it with my method. You just shake it. Like, just get a PVC pipe and like some diatomaceous earth and shake it, and you charge the diatomaceous earth or the sand or whatever you're using on the opposite end of the spectrum of the PVC pipe. Just look at the series, and whatever container you just use an aggregate that's on the opposite end. And the reason it's got copper tape is so that I can ground it to keep whatever charge is on the aggregate, so that the container would be the opposite charge. And once I ground it, the aggregate's going to maintain its charge while this becomes neutral.
So you just you're trying to take the charge off of the PVC pipe while building the charge inside it.
Yeah, you're trying to keep the charge on the aggregate and neutralizing the container, so that whenever you pour the aggregate into the mold,
it doesn't change
it. Right. So you don't have to melt or do anything. You could use caulk to try to use as a binder with that, and you wouldn't have to melt it.
Interesting.
You want to pull, so you want to pull a negative vortex on this thing. So basically, you want to have it sucking the air out of the system while it's shaking, so that when you put the actual liquid in there that you're going to use the hardener, that it pulls into the system and fills the entire thing, and then you can shut both valves off while it's shaking, and then it dries in that position is what you're looking for. That way it sucks through the whole thing, and it's not just forcing it in, but you want it to suck through the whole thing. So it would be a lot easier to hold it in there in the exact spot that it's in. That makes sense to you?
There's I've contemplated, you know, using vacuum. You know, once you charge the aggregate, put in the mold, and then you add the binder, you could, you know, how Shawn does, then you could put it into a vacuum to ensure that the charge gets locked in. But then to even further do optimize it, you would be hitting it with a high charge as the binder solidifies.
Right.
Yeah, but the vacuum has to be in the tube itself that you're working in, not in the bucket.
No, once you charge the aggregate, you can pour it into whatever mold you want, and it'll maintain that charge as long as it's not grounded through a conductor to the earth. So if I charge some sand and I poured it into a plastic container, it will maintain that charge so long as it doesn't have a conductive path to ground.
Mm-hmm. So no metal containers. You want plastic. You want stuff
Okay.
that will not affect the charged particles.
Right. The mold should, I mean, you can get to the point of using metal conductors when you know what you're doing as the mold, but just start off using non-conductors and making sure it's not grounded in any way. And the aggregate will maintain its charge, and you can add the binder.
What's the best granular material, or should I read your paper again for building Electret?
I think titanium dioxide is one that I would try. Aluminum oxide is actually good, so I know Nathan would like that. Like aluminum oxide powder. But what you want is a powder, you know what I mean? Because that's what gives you the charge density.
What about Teflon?
See, Teflon would be on the opposite end. If you want a negative charge, you would do PVC, Teflon, silicon rubber, those types. And then if you want more of a positive, you would use like crushed up hair, glass, you know, so it's just the opposite ends of the series. But Teflon would probably be the best to get going for a negative monopolar electret, and crushed glass would be an easy way for a positively charged electret.
Interesting. I have to come up with an electroscope to measure the high voltage field density.
I just received today an electroscope so that I can just mix it into the cups and set it on top, and then the meter will deflect.
Nice.
Yeah.
Do you have like a jewelry or stone tumbler or paint shaker?
No, I don't. I have a large diameter PVC pipe that I was going to use, and a drill just to tumble.
Makes sense.
Because you want the container to be the opposite of the aggregate whenever you're shake charging it, or acoustically vibrating. So yeah, that's why I say, like, so if you're going for a positive electret, you want to use something like sand or crushed glass, but the container needs to be PVC in this case, or Teflon, or something on the opposite end of the spectrum.
How do you determine what's opposite?
Sorry?
How do you determine what's opposite between the container and the contents?
The triboelectric series. You have to look up the triboelectric series. Like hair has a tendency to become positively charged when it's rubbed against a rubber balloon. And in this case, the rubber balloon is the negative side of the spectrum, and the hair is the positive spectrum. And the larger the divide of those two, the more likely the charged, what charge you're going for is going to occur. Each will have, after the triboelectric charging, each will have a charge. And that's why, grounding the container, you can keep the charge in the middle of the container.
Yeah, as long as there's no conductors, all insulators. But I'm curious again, if I were to say, hey, I want to put a positive and a negative, what if I think the PVC is positive and I think the let's say aluminum oxide was negative. What's going to tell me that's not right? Is there a table?
Yeah, it's a triboelectric series.
Series? I'm
It's
sorry.
Yeah, it's called the triboelectric series. It's a table that'll show you the highest positive all the way, like wood's in the middle, wood's neutral, and then on the bottom you get Teflon. So from the top, you would have like titanium dioxide. In the middle, you would have wood, and on the bottom being negative, you would have Teflon.
You are the man. I see it now. Oh, it's color coded. You're brilliant.
Okay.
There's a lot of smarts behind that big beard.
So I got a question here for you. Are the electrics completely static? Someone was asking,
It's
they keep
like-
asking about if there's static electricity or.
Yeah,
Completely.
yeah.
On
It's
steroids.
just like pulling clothes out of the dryer kind of thing, but then you like hit it with some adhesive spray to lock in the charge, you know. But
that's a good analogy.
Yeah.
you know,
I like the ant socks.
yeah,
That's interesting because doesn't John Hutchinson, one of his processes for making his battery is shaking it, isn't it?
I
He
don't
shakes it
know.
and then he sets it.
It would make sense. Yeah,
It would make everything
I-
seems to be together if that's the case.
yeah. I've thought of ways to make batteries easily doing something similar. Yeah,
He kept some of that to himself though, so we don't know exactly what he was doing, but
Right.
that could have been part of the process if he didn't mention it, like publicly at least, you know.
right. Yeah, Hutchinson, I think he was getting his effects because of Electrets. I heard one comment, I wish I knew it was on this channel, of one of Hutchinson's methods was taking candle wax and melting it and holding a conductor above it while having a charge on the conductor, and the wax, as it solidified on the conductor, would produce an electret.
Oh.
So he was definitely into that. And by using the microwaves going on, if you have magnets and electrets and you're hitting it with microwaves, you're messing with the fields, you know.
I'm still not clear on the magneto electrets.
It's just combining a magnet with an electret. And
just combining a magnet?
Yeah. You can buy an off-the-shelf magnet and then sandwich it. Like, say if you had a disc magnet and you sandwiched it with a positive and negative on the bottom, that would be one example of a magnetoelectret. And it could be yeah, and like since magnetic fields and electric fields, we were saying don't want to be parallel, the Ghostbuster field. If you make a magnetic field and electric field parallel, they'll want to vortex. They want to be perpendicular to each other.
Oh, and their vortex can be work.
Exactly.
Wow. And a magnet loses 10% of its strength every 100 years. So, I mean, that's a stable force for some time.
Yeah.
Okay, I'm too excited.
Yes, Magneto is a force to be reckoned with.
I am
once you start
Hold on. If you induce a magnetic field and it's contained already in something, would it stay in there in a small level or at all?
Just like a permanent magnet, right?
Well, say I took some wire and ran some electricity to it and got a magnetic field, and then I encased it in something. Would it stay in there?
If you're using
would it hold a small?
Just like how you would make a magnet, yes.
Oh my
That might be why Gerald's coil is getting evos in it. It's continuously eating through his epoxy because it's holding the charge in there with that epoxy.
Huh.
Yeah, the epoxy is a good charge.
Oh, wow.
Yeah, interesting.
My brain.
I know it's a lot to take in, but if you take a moment and start thinking about what you can do with monopolar electrets, it's a game changer.
Possibilities are endless. When you said monopole, I thought, oh my goodness, Google monopole magnet. and listen to the scientists say, this is all we can do, but it doesn't exist. And then apply that thinking to a monopole Electret, because I think that will at least spur some creativity of possibilities.
Right. Yeah. And Shawn, what I want to try with you is a pendulum made of two different, like one positive bob and one negative bob, and see if the time is different, from the swinging period. Since there's 100 volts per meter in the Earth's atmosphere, there should be deviation between the positive monopole and negative monopole.
All right, I'll add it. I'll add it to my experiment list. Yeah.
Nice.
And I think that's how Egyptians were dowsing, because gold, it will pull a negative electric. So like if you had a rubber band and there was mineralization, you could feel like a slight tug, so dowsing, if it does make sense if you're sensitive enough to feel those forces, very small forces, unless you use electrodes.
Sounds good.
Wow, that reminded me of something. It's like clicking in my head somewhere, and I can't put the two together. But it had to do. Oh, I think I know what it is. I can't talk about it. It has to do with the charge and how your oh my God, the plasma in your blood holds it. Anyway, I'll talk to you about it later. It's more interesting subject that I can't really go into, but yeah, it totally makes sense.
Yeah, I'm trying to wrap my head around the electric charge field. It doesn't move, right? It just goes to all points in space.
Yeah. Physically they say it stretches to infinity, but it's a longitudinal wave and not like magnetic waves they'll circle back on themselves. So
exactly. Exactly.
With unless like the conventional wave making an electric, the electric fields is within the dielectric. So on the outside, the electric field does curl around like a magnet, but with a monopole, it's just like, just like a sea urchin. It's
a lonely electron. Yeah.
So is that how?
Great analogy, sea urchin. That's the best analogy.
Right. Is that how MIT moved from saltwater to freshwater? How they split them is they just use the charge density of it. So the salt water to hold a different charge, and the regular water wouldn't hold a charge, and they could split the two.
You can use electrets to, like, say if you had salt water, if you heated some sand and shook it and put a positive charge on there, and you had salt water, strictly just brine, the chlorine will want to be more of a negative charge, so it would be attracted to the positively charged sand. If you heated it up and threw it in the water really quick, there could be some separation of sodium hydroxide and the chlorine evaporating off. If you make sure it's completely dry and it has a huge charge density and just threw it into the brine water, there should be separation. You should get sodium hydroxide left with an evaporation of chlorine coming off.
Right, because they have layers of water that will not intertwine with each other because one has so much salt in it, and one has no salt in it.
That's osmosis, though, I think.
Okay. But they're in the natural formations, though. In natural formations in water, they won't do together. Just like the ocean, certain parts of it will not mix. They'll stay separated. I'm just wondering if charge plays a part in that. If they have a different charge density, so they won't mix.
I think charge plays a part in pretty much everything.
Yeah. Yeah.
You know what I mean?
It plays a part, and we can't put our hands through these walls.
Yeah. Once like electrets are available, just like magnets these days, this world's going to be completely different.
That means we got to make really strong ones and show them off.
Yeah.
Yeah. We'll have to make negative and positive ones. Yeah.
Right. And if they can only get 10 to the -8 coulombs, I can get like a coulomb of charge very easily. You know what I mean? It's a game changer. But I want everybody, you know, like I said, being the intellectual property holder does not mean I'm trying to keep this or you guys aren't welcome to do it. I think if we focus on something like this and just make like a desktop toy that spins, you know, for some CEO, the new CEO desktop toy.
I'm telling you, monopole is going to be huge.
Yeah.
Huge.
Yeah. Once you get the idea of making one and it comes out in the lab, it's easy to amplify this stuff, is what it sounds like. That'd be an easy path to get this right.
Right. And when it becomes more mainstream, you know, like Plasma Channel discussing it and stuff, there's going to be more interest in the triboelectric series and people trying to find the most positive and most negative. And, you know, the material science will eventually kick in where there's huge negatives and huge positives, not just crushed glass and Teflon.
Yeah.
It's like changing your anode and cathode in a just a simple saltwater battery.
Yeah,
they came up with all kinds of different ways to do it and see which one's the best.
Right. It took them a while to discover the neodymium. You know, it was just melting iron at first and hitting it with the magnetic field. But through material science, now neodymiums are just crazy strong.
Yeah. Ooh, we're going to have to work on this. I'm going to have to work on this with you guys. This is awesome.
Yes. I'm excited about it. And it's easy, you know.
I was going to ask a quick question. What do you think of me hitting it with 1 to 12 to 24 inches of the Van de Graaffs, as in hitting the material? You think that's strong enough? I saw that you had a little high voltage generator that you can pick up on Amazon.
Yeah, I'm actually not trying to arc at all. The arc is a waste. I'm just trying.
Right.
You don't need higher than 10,000 because I'm not necessarily looking even to ionize the air. And past 10,000 volts, it will start ionizing the air just by sitting there. And I don't necessarily need above 10,000 volts at this point.
Oh, I didn't know that. And I could not. Well, I would need to have some space for the discharge because it's a Van de Graaff generator. But I see what you're saying. But
yeah,
no. You want a DC flyback and you want to control the distance so you can get the dielectric out of it. You don't want it to spark at all. You need to pull it apart far enough where you can just get the charged state. That's all you want. And then lock that in position and you're set. Then do the shake. And it always stays at the same charge in the shake. Yeah.
Yes, you want to.
You don't think a pulsed with a little bit of arcing, but
no arcing.
DC pulse wouldn't help?
The arcing was used in, you know, conventional methods now, you know, coronal discharge methods and stuff. But this is completely different because you're going for a monopole. You're not going for a dipole.
Right.
Because the dipole will be a combination of two monopoles.
Right.
And, you know,
it's going through my brain right now. If you take that PVC pipe, you can put such a heavy charge on that thing by using 2 DC flybacks in series and then connecting it top and bottom. You could throw a massive charge on that thing and you wouldn't spark one bit.
Right.
But the flybox have a pulse DC.
Oh, no, because I've done that experiment and I can get it to go one way or the other. So you can charge in a direction too. Yeah. No.
I said, even that's why I got just a little taser module because I'm not even looking for 10,000 volts with a huge charge density like this is really sufficient. It's, you know, you don't necessarily need humongous voltage. 10,000 volts is just from a little taser module. Mine says it can get 400 kV, but I looked it up. It's probably like 20, 30 kV. But the reason I use a pulse width modulator is because I can control the voltage with the pulse width modulator. The faster the frequency that I send through the taser module, the lower the voltage. So I can adjust the voltage using a pulse width modulator to drive the taser module.
But shouldn't you be having a DC so you're pushing
It is-
everything in
it's
the same direction?
It's a pulse DC output on that.
Is it a pulse DC? There is a diode on the output? I didn't know that. You're talking about the one you just
Yeah.
showed us.
No.
Yeah.
Take
Okay.
take your ZVS, and
Got it.
that
Got
thing
it.
sparks over too fast. You're going to get a lot of sparks out of that, even at distance.
Yeah, that's why I had the pulse width modulator on it.
Hold on.
Ah,
I got something better for you. When you take your ZVS, okay, put your high frequency diodes on it, just like we're doing for our Tesla coils, and run that at distance. It'll put charge right on the PVC for you, no problem whatsoever. That it'll do it in seconds, and you will not get spark over. I've just run the test recently.
The reason I chose this is because for under $20, anybody can get started with it, and it really is sufficient. It really is sufficient. I don't need a ZVS. I don't need a Tesla coil. I mean, these taser modules are basically what Tesla coils, the end product, and it's light. So when we get into levitation, it's a great power supply because it's so light for high voltage and stuff.
But the problem with it is, at a distance, it'll look like it's not doing anything in the dielectric, and then once it'll start to do a heavy spark, it'll stop for a while, and then it shoots a spark across it. So I've had it happen several times on me with those things.
You know, I get you, but I could put like any insulator between the two outputs of that to prevent all arcing. Like, I think you're like on the two, since I'm making monopoles, the two terminals can be any distance apart from each other. So like I can put one on one side of the room and one on the other side of the room because I'm making two monopoles, and I can combine them for a dipole if I want.
That's awesome.
So yeah, I don't know if you're getting it. Wherever the mold is, I can put insulation between the two. Like I can charge a negative and positive at the same time and put them on two separate places of the room, and there would be no arcing.
Okay.
The only thing about arcing is you're going to lose some of the energy by ionizing the air when that could be pushed into a pressure, if you will, to align the granules to be monopole. So it's just a waste when it comes to the discharge, right? It's not if you had discharges, it wouldn't work. You have discharges, you're really not applying the right pressure.
It's not that it wouldn't work. It's just an inefficient way of doing it. It's just
Exactly.
like conventionally. Yeah, I mean, it's not detrimental to even if it arcs, it's not gonna ruin the product. But I mean, you just don't need it. So, you know.
So let me ask you this so I can get it right in my head if I'm getting it wrong. If I took say a foot long pipe, right, of PVC, and I put a cap on, I put a bolt in the cap, and I put this little charging unit on there with pulse, it's going to pulse the charge in that 2 foot, in that foot, just the same as it would in a 2 foot length. As long as it overwhelmed the charge on the surface. Is that what you're trying to say?
Well, I'm only using one end of the output at any given time.
You're not using both?
No.
Yeah, like I said.
Now I get it.
I'm doing it monopole, so I don't need
You're all negative in it or all positive.
Mm-hmm.
Yeah, like
now
conventional. Yeah, I'm using one terminal at a time.
It's so brilliant. No one thinks like this.
Gotcha. We all think in one circuit, so we're thinking negative to positive or positive to negative. You're thinking just one over here and the other one's unimportant. Okay, I get that. I've done that.
Yeah.
And I think that's the one with the most opportunity.
Yeah, that's why I say you could do both at the same time and just put them wherever you wanted on the end of each room, and they won't arc. You know what I mean? Because you're making one negative electret and one positive electret. You know, it's open circuit. There's no finished circuit. You're using just the positive charge and the negative charge to charge it while it's because it's
Now I get it. Okay.
Cool.
You know, I did something that a little off than that, but I did it. It's a little different. I took that water and I charged it all to the positive charge along with the bowl itself. And when I put the negative up to it, it would spark on everything because of the it was all now one charge on it. It flipped the whole thing. So yeah, I get it. And I've done the all negative and all positive on things. It's like on, for instance, on my melamine table, if I just hook negative on a piece of foil, it'll suck to the table because it's charging that table up with that charge. So if you do the positive to it, it goes all positive.
Exactly.
No, I get it. It's the same thing. Yeah, all right. Now I get it. Now I'm in the right ballpark.
If I had a piece of Teflon, if I had a piece of Teflon, I could throw it onto a glass window and it would stick, just like a magnet on a fridge.
Mm-hmm.
That's crazy.
Yeah, that's awesome.
Yep.
Now it's even better.
You get me?
Yeah, because I can pull those effects easy.
Yeah, think of like the conventional electors. They're trying to close the circuit. We're trying to just make one positive and one negative and then sandwiching them together if we want a dipole.
Dude, the sky is endless. Nice work.
When you start thinking about it, you're going to be coming up with some crazy stuff. You're going to wake up like after a dream, like, oh my God, I got to write this down. You know, it's crazy when you really start thinking about it.
It opens up so many doors. It really does.
But that's why I want like a little taser module, because anybody getting into the game can get one of those, and that's really
cool. Yeah, $4, $5 on Amazon.
PVC pipe and sand at Home Depot. You know, so it's really easy to get going.
Well, if you use the ZVS, you can control your frequency by the cap that you put into it.
But I control it with the PWM.
You're controlling it with the PWM. You're changing the frequency on the PWM to do it?
Yeah.
It's on the input power.
Yeah, because, okay, I get it. You turn it on, you put the frequency on there of the PWM. Okay.
Yeah. And then that drives the taser module, and that's all you need for the, you know, as the high voltage supply. And it's light, you know, so whenever I get into lift and stuff, it's great for that because it's so light.
And it only needs a few volts to power up the high voltage generator.
Yeah,
that's
mine will go
AA
up to
battery.
Volts, but it goes up to 9, or like I use 9-volt batteries, but it can go up to 12-volt lead acid. Yeah. But I just use little 9-volt batteries because those are light too. The lithium ion 9 volts are really
on
light.
that taser module.
Nice.
My taser module here will take a lead acid 12-volt because it's a higher voltage one, but they usually go from 3 to 6 volts.
Yeah, okay. I got the 6-volt one, so you can only use 3 AA batteries on it max.
Yeah, and
or else it blows up.
in series, like you can parallel and series these modules too. You know, you can get whatever voltage you want.
I have to run. Can we have Vortex on next week?
Yeah, if you want to come on next week, absolutely.
And I'm going to be working hard.
I love it, Shawn. I always love chatting with you, buddy.
Hey, love you, brother.
You're one of the best experimenters. You're just such a great experimenter and builder. I just love your work, man.
Thank
I'm a
you.
fan for life.
For sure. I got to run too, guys, but I really appreciate everything.
So is that okay? You want to come on next week?
Yeah, I'm starting to feel better. I do. I would like to come on. I'm trying to get stuff going on, you know, trying to get a channel and stuff. But I think this will lead somewhere where we can like start going to the moon with little drones and a little like if we really put our
Nice.
minds together.
Yeah,
I'm
I
excited.
agree.
I'm gonna do some
But
charge
yeah,
experiments this
I'm
week
probably
just
gonna
to
head
find
off
out.
too.
Well, let's set that up.
I'm
Next week
excited
we'll
that-
have you in. I'll make sure I put it on the thing so that we're good to go. And Wednesday we'll set you up with the invite so you can come on and hang out with us and talk to us about it.
Yeah, Wednesday would probably be a good day for me
Nice.
if that's
What
possible.
can we call you?
We call you Vortex or Miscellaneous still?
My real name's Brent Jarvis, and I went by Jarvis in the military. And it just
Jarvis?
Yeah, Jarvis. That's my real name.
Okay.
love
Well, then
Jarvis.
we'll call you that.
Alrighty.
That works
All
for
right,
us,
Jarvis.
man. Yeah,
Thank you
right
guys
on.
so much. I'm probably gonna get off with you guys. Try to get my throat better.
Oh,
Yeah.
sure. Take care of your health.
Not a
Thank you.
problem.
Thank you.
All right, guys, it's at the 2.5 hour mark. We're about done for the show today. I want to thank everybody, Shawn, Ben, Jarvis. It's awesome having you guys here.
Thank you.
We'll see you here on next Wednesday. Shawn and Jarvis will be on, and that'll be awesome, man. So I'm going to work on some of these things this week. You got me going.
Yeah.
Now that I figured out how it's working, I'm going to put it together.
Genius Jarvis.
Yeah, there you go.
Much love, guys. Take care.
All right, guys. Have a
Much
great
love,
night. You guys have been awesome. Thank you in the chat.
Night.
Good night, guys.